Good day, I'm Norman Wobbener. So this is a joyous occasion. We've now reached number 200 in this series on the foundations of mathematics. Today we're going to look at what we might call mission impossible. The task of factorizing our favorite big number, z, into prime factors. So z is the number 10 triangle 10 plus 23. And if you've been watching at all any of the recent videos in this series, you'll be rather familiar with this number. But let me remind everybody, it's a use of a hyperoperation, 10 triangle 10. It means 10 to the 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 10. A string of 10 tens, each an exponent of the previous one, plus 23. So this is a humongously big number. And we claim that this thing does not have a prime factorization. So this is in direct opposition to the standard fundamental unique factorization theorem, also called the fundamental theorem of arithmetic. So in this video, what we want to do is we want to talk about particularly the problems with z. So first of all, we'll talk about the difficulty of even discussing or defining prime numbers in the range of z. We're going to have a very good look at factorizing things of the form 10 to the n plus 23. I want us to get a really good solid intuition for what typically happens when we look at factoring these kinds of things, especially as n gets bigger. We'll only be able to go very, very short distance up to z, but still we'll make a little bit of progress to get some intuition. And we'll see that the difficulty involves not just getting prime factors, but also in obtaining the quotients of those prime factors. And it's really the blowout in complexity that ends up defeating us. And this will really bring to a fore, I think, this fork in the road that mathematics is going to have to deal with. All right, that computational reality goes in this direction, and idealism goes in a different direction. We're going to really have to face the music here and make decisions about which way we want our subject to go. So let's introduce this rather suggestive terminology of dark numbers, which I think is amusing, even though it may not be very precise. So let's talk about dark numbers less than z. So z is a very big number. Okay, and if we think about what we were talking about when we were discussing complexity of numbers, we made a rough estimation that if we think about the very smallest possible cubes that we possibly could use to write something down in, say a Planck cube, maybe 10 to the minus 30 or 10 to the minus 35 meters wide, very, very small, there's maybe around 10 to the 200 Planck cubes, something like this, filling the entire observable universe. So if we imagine that we're able to miraculously somehow write at that infinitesimally or almost infinitesimally small scale, then it gives us a kind of a bound on how many possible expressions we could possibly even think about writing down. So let's suppose that for the sake of argument that our keyboard has 1,000 symbols to choose from, and so we could put any one of these 1,000 symbols in a Planck cube. Then there will be 1,000 to the 10 to the 200 possible expressions that we can write down, filling the entire universe with these symbols, one for every little Planck cube. So of course this is vastly more than we actually could do, but some kind of bound. And it's easy to see that this thing is much less than 10 triangle 4, which is 10 to the 10 to the 10 to the 10. Okay, so 10 triangle 4 is a convenient short limit on the number of possible expressions that we can write down in our physical observable universe. And so it follows that this is also a bound on the number of numbers that we can write down, because numbers are just particular kinds of expressions. And then we just obviously observe that z, which is 10 triangle 10 plus 23, is very, very much bigger than 10 triangle 4. And so if we believe that there really are numbers from 1 all the way up to z, if we believe that actually makes sense, that there are natural numbers, 1, 2, 3, 4, you can go all the way up to z, then it follows that the vast majority of those numbers, okay, cannot be expressed in our observable universe. no matter how clever or concise you write, no matter what kind of arithmetical system that you devise, because there's just at most 10 triangle 4 possible expressions that you can write all together. Right? So the vast majority of numbers less than z, natural numbers, are lost to us. They're invisible to us. We can never actually access them. We can call them dark numbers. I know this is disconcerting, okay? This is a strange kind of way of thinking because it's contrary to our usual sort of inductive idea that things just march on pleasantly in a similar fashion to what we're used to. But this is the reality. Computational reality is that most numbers, if you really believe in such things, less than z, are invisible to us. Of course, it really, the logical consequence of this is that we should actually be skeptical about the idea that it makes sense to talk about all the natural numbers less than z, to believe that there are actually z of them. But I hope you can see that this problem of these dark numbers is going to directly affect this question about the factorizability of z into primes. Because if we look at all the numbers from 1 to z, and we want to factor this big z, well, there's going to be a lot of prime factors typically. And now we run into the sort of unavoidable likelihood that most of those prime factors are actually going to be in the dark range, because after all, most of the numbers from 1 to z are dark numbers. They're beyond us. They're too big to even write down. So the primes are also going to have that problem. In fact, even to define what we mean by a prime number, even in this limited range from 1 to z, is now much more problematic than it appeared to when we first just thinking about little numbers. Okay. So what could it mean for a dark number to be prime? Let's suppose that we're playing this game and we now believe that there are these numbers that we can't write down. It's a dark number. What does it mean for this thing to be a prime? Let's call this dark number that we're considering a d, kind of a Gothic d, to distinguish it from the usual kinds of natural numbers that we usually like to talk about with nice n's or p's or q's. So here we have this Gothic d. It's a dark number. We can't actually write it down, but we're pretending that we can contemplate it. Okay, what could it mean for a dark number to be prime? Well, the definition is that we need to decide whether this number is divisible by any number less than it. It means we have to go through all the numbers less than d and see if any of them divide d. But how are we going to do that? Because most of these numbers that we're considering here are also likely to be dark. Okay, so we can't access any of them. So how do we check whether these dark numbers that we can't access divide d, which itself we can't access? So what does it actually mean for d to be prime? This is highly problematic. My computer is sitting and listening to this conversation, and it's shaking its head, saying, wait a minute, none of this makes any sense. My computer is thinking something like, sorry, but if it can't be written down, then it is not a number. Okay, maybe my computer is not actually saying that. But if computers could think and express themselves, and probably in a few more years they'll be able to do that, we'll be getting this kind of message from our computers. They'll be telling us, wait a minute, what are you talking about? If you can't write something down, then what possibly are you talking about? Or are you doing poetry, perhaps? But wait a minute, Norman. In modern mathematics, don't we have a lot of freedom? Can't we just invoke our abstract thinking and our notation to deal with these kinds of things that you're wrestling with in a very hands-off kind of fashion? For example, can't we just write down stuff like this? Let H be the set of n natural numbers such that n is less than or equal to z. We just write this down. This is the set of all natural numbers from 1, or actually from 0, up to z. This notation captures the idea and completely finesses the issue of whether or not there are actually dark numbers and how we deal with them. If we want to be a little bit more specific, or maybe not use such fancy kind of language, we can just write down the set 0, 1, 2, dot, 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 z. This invokes this idea that here in this set are all the numbers from 0 up to z. This is not an infinite set. So we're not talking about my usual objections to infinite sets here. You can see that there's already something very problematic with this large set. Because in this range here, there are these vast tracts of numbers that we have no possible hold on. It's just a complete sea of blankness to us. So what are we talking about here? But we can go further in modern mathematics. This doesn't stop us ordinarily, so we just carry on and write stuff like this. And now let's let P be the set of P in H. H is the set that we've just defined, such that P is prime. Bingo! With one stroke, like a magic wand, boom, suddenly, poof, there, all the primes less than z are now suddenly created out of magic. Fabulous, isn't it? Or if we want to be a little bit less fancy and just write them down, we just go 2, 3, 5, 7, 11, 13, dot, 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 up to P of z. What is P of z? Well, it's going to be the largest prime less than z. We're just allowed to write stuff like this down. P of z is the largest prime less than z. Our computer would not understand any of this. Incomprehensible. And this is also not at all in keeping with the approach that we have been championing towards data structures. So for us, if you want a set, you are obliged to write it down. There's no 3 dots in the middle that obscure all kinds of vast tracts of inaccessible objects. You're obliged to write them all down. And if you can write them all down, then you have the set, or the M set, or the O set, or the list. And otherwise you don't. Okay? Very, very big difference between the way we're trying to promote mathematics here in this Math Foundation series and the standard procedure that you find throughout the rest of the mathematical community these days, more or less. There really are very serious questions here that people ought to ask. And it's not just about only infinite sets, okay? There's serious questions just about what happens when things get big enough. Once things get big enough and we don't have to go to infinity, we already run into problems. Our computers run into problems, and so do we. Okay, so let's leave this question of dark numbers and all these sort of fanciful notions aside. And let's return to something more fundamental and think about things from a computational point of view. Let's ask rather what we can actually do computationally solidly. And having our computers support us so that we're thinking along lines that are parallel to what the computers are doing, not diverging in different directions. Okay? This is increasingly going to be a litmus test in the mathematics of the coming century as to whether you're on the right track or not. Okay? Are you diverging from what your computer can do? Then maybe you should think about where you're going. Okay, so let's return to the question of factorizing z from a computational point of view by starting from the bottom rather than from the top. Okay, so let's be more modest, a very good place to start. Let's start with a lot simpler kind of situation and see how far we can go towards factorizing z. Okay, very, very good, powerful idea. So let's start very modestly with 10 plus 23. That factors as 3 times 11. And then let's up the power 10 squared plus 23. Factors as 3 times 41. And I'm going to go through a list of these kinds of numbers. So it's always a power of 10 plus 23. I'm going to stick to that kind of framework and see what happens. Now this is very parallel to what I was talking about some time ago in the famous math problem series. In fact, the first of that series, which was all about factorizing z. So there's a lot of overlap in what I'm going to do now with that video, but that's all right. Okay, these are, I think, interesting ideas that it's important that those following this series have some intuition as to what actually happens. This is not something that most of us have a lot of familiarity and experience with. We're quite comfortable with, factoring small numbers in the hundreds and thousands, but when we get to bigger numbers, we don't really have a good sense of what typically happens. What can we expect, and what can we not expect? So we want to develop a little bit of intuition. So we're going out into the field, as it were, to perform some actual observations, record some things. Okay, so various powers. 10 squared plus 23 is 3 times 41. 10 cubed plus 23 is 3 times 11 times 31. 10 to the 4th plus 23 is 3 times 13 times 257. 10 to the 5th plus 23, 3 times 7 times 11 times 433. And then this one, 3 times 333, 341. 3 times 11 times 19 times 41 times 389. 3 times 2293 times 14537. 3 times 11 squared times 61 times 45, 161. And here 10 to the 10 plus 23, 3 times 13 times 29 times this prime. 3 times 7 squared times 11 times this prime. And 3 times 41 times 211 times this prime. So can we see some kind of pattern? Is there some kind of predictability? Well, obviously there's a factor of 3 everywhere because the sum of the digits is always 6. And if we see this 11 here, we see it in a lot of other places, and it's not too hard to notice that it seems to appear every second one, and at least here it appears twice. And the next factor, 41, does that appear anywhere else? Oh yes, it appears there again. How about, say, a 13? That appears there, and it appears there again. So maybe there's some kind of repetitive aspect, at least some kind of periodicity in here. But of course there's something also that's very unpredictable because these bigger primes are sort of popping up out of nowhere, as it were, and it's very hard to predict, what this prime is if you had just up to here. All right, let's go a little bit further. So we'll keep this one in mind, and I will quickly go through a few more. Okay, so let's have a look at some further ones. 10 cubed plus 23, we have this factorization here. And then the next one, this one here, this 10 to the 15 plus 23, that's rather curious because the prime that's involved here is 30, 30, 30, 30, 30, 30, 31. That seems rather strange. And then we get, some kind of patterns. Of course, the primes get bigger, but there seems to be quite a propensity to have suddenly big primes. Big prime there, there's another big prime there, another one there, another one there. There's always some pretty decently big primes. Here there's a pair of bigger primes. Here we have quite a few smallish factors and a bigger prime. Here are a few small factors and then a bigger prime. And I guess we observe these other factors, the patterns of 11s every second is appearing again. How about 41s? Yeah, there's a 41 there and another 41 there. It appears to be some kind of regularity with the 41s. And maybe we've seen other ones too. There's a 13 there and a 13 there. There's a 17 there, and there are any more 17s? I can't see any. But certainly there's this idea that once a prime is on the list, then it will carry on appearing at regular intervals. And you might like to think about why, or first of all, is that true? And if so, why? That's a nice exercise to think about, what kind of patterns there might be in this list. It's obviously not entirely random, but there might be some interesting structure and things to observe. For example, one might like to explain, why is this thing appearing? Is that just a coincidence, or is it somehow related to the numbers here? Let's carry on a little bit with some higher ones. Okay, so we're not going to go through all the powers here, but say multiples of 10 at this point. So 10 to the 30 plus 23, we have this thing here, a very big prime there. 10 to the 40 plus 23, a few small ones, and then two biggish ones. 10 to the 50 plus 23, this times, now this one here is all one big prime. Okay, if there's no multiplication sign, it means that this is a wraparound. So that's all one very big prime. 10 to the 60 plus 23, we have this factor, a medium-sized one, and then a long one all the way up there. 10 to the 70 plus 23, a few factors, and then a medium-sized one, and then another medium-sized one, and then another medium-sized one, and then a bigger one. Okay, and just a few more. 10 to the 80 plus 23, a few small factors, a medium-sized one, and then a very long one. And then 10 to the 90 plus 23, there's a few smaller ones, and we end up with quite a few sort of medium-sized ones. 10 to the 100 plus 23, this is one that actually defeats me and my computer. My computer spends an hour or two trying to work this out and doesn't seem to be able to do it. But this particular factorization, thanks to Giorgio Coniglio, who offered it up as a comment to my Famous Math Problems 1, where I basically asked for the same kind of problem. So here we have a couple of factors, and then we have this thing up here, and then followed by this rather long prime. So how big are these ones? That's maybe a 10, 20, 30, about 30 or so for the first prime, and 10, 20, 30, 40, around 50 or 60 digits for the second prime. Okay, I think it's interesting even just to look at this kind of pattern. I mean, it's a way of accessing some interesting things that former generations had no possibility of doing. Right? So Gauss would have loved to have a computer to be able to investigate factorizations like this. And I think it's great that we can do this. And I want to encourage people to think of it as an empirical kind of domain. It's like we're botanists and we're on a new island. There's all these interesting species and things to look at and observe and gather data and stare at things and try to make some patterns and theories. There's probably relatively interesting observations to be made here, maybe some that are on the surface, maybe some that are deeper down. And so maybe some of you who are programmers might like to program what these kinds of particular numbers factor. So you can go through these exponents one by one and make a list of a couple hundred or 1,000 of them so that we can sort of stare at things and see what happens. But I think we can see at least some features that are going to point very clearly to my main claim. Okay? So my claim is that as we up this exponent here, okay, the problem is that we're getting these big primes. And this thing here is relatively small complexity. Okay? It's only, a complexity of less than 10. But the primes that we're getting are high complexity. It's very unlikely that this prime here, for example, has complexity that's significantly less than 60. All right? And if we jack up this exponent here, replace the 100 by 1,000, or by 10,000, or by 1,000,000, or by 1,000,000,000, well, we can expect this to really blow out on us. That these things here on the left-hand side are very compact and concise. They have low complexity, but their factorizations involve high complexity. So the process of factoring sort of blows out in complexity. That's the essential problem. That's the essential problem why Z is not going to be factorizable. Because although we can write Z very compactly, there's no way we're going to be able to write the various primes that appear in its factorization, even if it had one, in a reasonably concise way. They're going to be these things that look like this, but this is just baby stuff compared to what we can expect as we jack up this exponent here. And you can see there's even a huge distance to go from a factor or an exponent of 100 here to an exponent of 10 triangle 9. That's what's involved with Z. Okay, this whole thing is going to just blow up on us. And where it does so It's hard to say. I mean, our computing powers are definitely going to get more impressive, and in years to come we'll be able to go further than we can now. So it's not possible to say we'll be able to go up to this point and no further. Okay, but we can confidently say that we're not going to be able to get to Z. We're just not going to be able to factor Z. That's just the reality of the mathematical world that we live in. It doesn't matter whether we like it or we don't like it. That's just the way things are. But that doesn't mean that we should give up on Z. Z is still very interesting to study, even if we cannot arrive at a full picture of it. That's okay. So we know already that Z does have some prime factors. Joel Sjögren and other people have found them up to a certain point. So we know it has factors 3, 13, 139, 673, 18301, 400,109, and this one 279,97373. And then of course there's some quotient, and we have not a very good idea of that quotient. Now, I think it's a major challenge for us to find more prime factors of Z. And this is a challenge, this is a mathematical challenge that will live through the ages. Okay? So long after most of the standard problems that you know about in mathematics, the Riemann hypothesis and the twin prime conjecture and P equals NP, long after those things are solved and completely settled, this will still be an open problem. An endless amount of work can be directed into this effort. Of course, it'll get harder and harder as we go. I mean, eventually people will find very, very big primes, and it'll be humongously difficult to find even one more. Okay, but no doubt there will be big prizes in centuries to come to find more and more factors of Z. Am I right, mathematicians of the future? Okay, so this can be tackled by modular arithmetic. So we can look for prime factors by ideas of modular arithmetic, of divisibility. But that's different and additional to actually computing quotients. So after we've, say, found a certain number of factors, at some point we want to say, well, okay, what is the remainder that we have left? So this is another interesting aspect of this story, is how do we get control over the quotients? It's really a question of how much complexity is there when we divide one natural number by another. And this kind of thing was investigated by Euler, and we're going to have to look at some of Euler's thinking in this direction. It'll be an interesting way of shedding light on the complexity that we get that blows up in this quotient business. So to summarize, as we find more and more factors of Z, what's going to happen is that the complexity of the quotients are going to blow out. Okay? That's what's going to stop us. These things are going to get more and more complicated, and ultimately they're going to get too big to write down in our universe. And we're no longer going to have them. We're going to have them up to a certain point, and at some point they just go beyond us. And it's important to realize that this is a problem not intrinsically about the limitations of our computers. Okay, it's not about that. It's really about a limitation with the universe itself. Okay? The universe itself does not have enough space or power or time to factor Z. This problem of factoring Z is too big for the world in which we live in. So it's not intrinsically about our computers. It's important to realize that. It's not a computational problem in that sense. So it's very interesting stuff. So we are going to, in a future video, talk about this quotient story and look at Euler's contributions here. But I think it's an apt time to pause and have a little bit of celebration. So in my next video, I want to actually celebrate this 200 video mark and talk a little bit more expansively and generally about what I envision for the future of this series as we boldly go forth to try to set mathematics on a proper, much more solid foundation. I hope you'll join me for that. I'm Norman Wallberger. Thanks for listening.